Today, smartwatches are mostly being used as an extension of smartphones, but because they reside on the user's hand, which is the gateway to rich, contextual information across a wide ranges of tasks, they have the potential to become so much more. The watch's positions on the wrist make them ideal for catching micro-vibrations such as bioacoustics propagating through the user's hand, which could be used to classify hand gestures such as flicks, claps, scratches, and taps. The smart device also becomes a hub for data using the wrist device and external devices and objects connected via the human body as the network. Welcome to the Stanford Scholar presentation on ViBand, the high-fidelity bioacoustic sensing using commodity smartphone accelerometers. Let's explore the intricacies of this technology. Modern wearable form factors rely on accelerometer-based sensing for event detection. The APIs of most smartwatches limit the sampling rate to about 100 Hz, which is sufficient for detecting the orientation of the device. But existing accelerometers can go up to 4,000 Hz by modifying the smartwatch kernel. At such high frequencies, the smartwatch can even detect micro-vibrations. The primary research question concerns whether it is possible to convert common devices such as smartwatches into high-fidelity, accurate tools for measuring bioacoustic signals. Let's look at some issues in tackling this problem. The first problem is the effective usage of a great diversity of devices and types of data associated with them. The statistical complexity of detecting patterns of gestures, object detection, and structured vibrations make this an even greater challenge. Other techniques also suffer from noisy environments, affecting the reading while requiring more computation and data usage. The authors wrote a custom kernel driver for existing smartphones requesting data in high-speed mode. The entire pipeline is software only, which means that an existing smartwatch can do a simple software update to have enhanced capability. The technique enables novel interaction in 3 different application domains, namely gestures, object detection, and structured vibrations. The technique could be used to classify single and double-handed gestures such as flicks, claps, scratches, and taps. Combining them with motion tracking could enable a variety of input modality, such as buttons, sliders, and radial knobs. Even vibrations from motor-powered and mechanical devices such as dustbusters, guitars, and motor drills can be detected through their micro-vibrations. Structured vibrations enable the user to control the actuations of the vibrations. For this, the authors use a transducer to emit structured vibration patterns using 4 classical transmission schemes, as shown. Let's discuss the actual process. First, high-speed accelerometer data comes from the X, Y, and Z sources through sensors. For orientation independence, we fuse these signals and compute the FTT, which gives frequency information. Next, the signal is windowed and features such as power and statistical information are computed for ViBand applications. For the evaluation of this technique, 17 users with a mean age of 25 were selected to perform comprehensive testing of gesture recognition, object detection, false positive robustness, and structured vibrations. The results show that the device achieved 94% mean accuracy in both gesture recognition and object detection. Only 6 false positives were detected by testing on rigorous activities. Meanwhile, 4-phased shift keying shows the best bit error rate of 1%. In summary, ViBand is a feasible, low-bandwidth, energy-efficient sensing technique that is commercially viable today. This technology has proven to be robust in many situations and is efficient enough to be deployed in ultra-low bandwidth environments using very limited resources on the device. The combination of a low-power, low-feature, solar-powered wearable can augment the low-end smartphones and other devices for the next billion users around the world. Thanks for watching! Visit scholar.stanford.edu for more talks.